So far, we just used power series representation and find the convergence and find the function that they are converging to. Now, the theorem says if f has a power series representation, at a value like a, or we officially call it analytic function, and f of x can be represented by the summation of Cn x minus a to power n and start from 0 to infinity, and as long as x minus a is bounded between r and negative r, or the absolute value of x minus a is less than r, then the coefficients Cn, or the coefficients, are given by Cn is equal to the nth derivative of f at a divided by n factorial. So basically, if you have an analytic function, that function f of x, which is written as the summation of Cn x minus a to power n and start from 0 to infinity, which is written as c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared plus the rest of the terms can be written as c sub 0. Let us calculate each one of these for you. C sub 0 is the 0th derivative of f at a divided by 0 factorial. 0th derivative of f is nothing but f itself, and 0 factorial is equal to 1. So c sub 0 can be written as f of a plus c sub 1. Let's calculate c sub 1 for you. C sub 1 is the first derivative of f evaluated at a divided by 1 factorial, or f prime of a divided by 1. So you get plus, for c sub 1, you can write down the derivative of f at a and then multiply that by x minus a. You can continue this process. Let me move it a little bit over so we can write down all of these for you to some terms. This is 1 factorial here. And let me shift this a little bit to the other side so I can write down all of them. So c sub 0 is f of a, c sub 1 is f prime of a. You can find c sub 2 as well. C sub 2 is equal to the second derivative of f at a divided by 2 factorial. So plus the second derivative of f divided by 2 factorial times x minus a to the second power plus the rest of the terms. So basically, you can rewrite this as, so f of x can be written as the summation of Cn x minus a to power n starts at 0, goes to infinity, which is nothing but the summation of the nth derivative of f at a divided by n factorial times x minus a to power n and start from 0 to infinity. So as long as you have a function that has a power series representation, you can always find the power series representation following this formula. Perfect. So this is called Taylor series of function f at a. If you have a special case like a equal to 0, you call it Maclauren series. In the general case of a, f of x equals to the summation of the nth derivative at a divided by n factorial times x minus a to power n, and start from 0 to infinity, is called Taylor's series. In a special case, when a is equal to 0, f of x equals to the summation of the nth derivative of f evaluated at 0 divided by n factorial x to the n, and start from 0 to infinity, is called Maclauren series. Maclauren series. Hopefully the spell is correct. So if you hear about Maclauren series, it means that your a is equal to 0. When you hear about Taylor series, is just a general format when a can be any number. So let us use Maclauren series to find power series expansion for exponential function. What is power series expansion? Of f of x equals to e to the x around 0. Very good. We have a nice formula. We know that. If a function like f of x is analytic at a, then its power series expansion can be written as f of x equals to the summation of the nth derivative at a divided by n factorial x minus a to power n, and start from 0 to infinity. Or in simpler version, you have f of a plus f prime of a x minus a plus the second derivative of f at a divided by 2 factorial x minus a to the second, plus you continue this process. Let us begin, right? What do we need? We need f of a, f prime of a, the second derivative of a, and so on. E to the x is your function. F of x is e to the x. F prime of x is just e to the x. It repeats itself. This is a special case function that if you take the nth derivative of it, it's always equal to the function itself. But since the question says, hey, find the power series expansion around 0, we are using the Maclauren series. So since we are using a equal to 0, f of x is equal to f of 0 plus f prime at 0 times x plus f double prime at 0 divided by 2 factorial times x squared plus the third derivative at 0 divided by 3 factorial x to the third plus the rest of the terms. So what is f of 0? F of 0 is equal to e to power 0, which is 1. F prime of 0 is e to power 0 equals to 1. All of them are equal to 1. So f of x, which is your e to the x, is equal to f of 0, which is 1, plus f prime of 0, which is 1, times x, plus f double prime at 0, which is 1, divided by 2 factorial x squared, plus 1 divided by 3 factorial x to the third, plus the rest of the terms. So, power series expansion of e to the x is, e to the x can be written as the summation of 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus the rest of the terms, which in turns can be written in shorter version, compact version, which is the summation of x to the n divided by n factorial, and start from 0 goes to infinity. So let us recap what we did. We started by introducing a theorem. If f has a power series representation, or if f is an analytic function, it can be written as the summation of Cn x minus a to power n, where Cn, or the coefficients, can be calculated by taking the derivative of f, evaluating them at a, dividing them by n factorial. So we introduced the Taylor series. F of x can be written as the summation of Cn x minus a to power n. In special case, if a is equal to 0, well, you have Maclauren series. The question here says, what is the power series expansion of exponential function e to the x around a equal to 0? So basically, you're using Maclauren series. You're using f of x to be summation of the nth derivative of f at 0 divided by n factorial times x to the n. We know that the function f of x is analytic. F of x is e to the x exponential function. It's continuous everywhere. There is no issue with this well-behaved function. And if you take the derivative of this function, all of them are equals to e to the x. So it makes it very easy for us to do the calculation. Since we are using Maclauren series, f of x is f of 0 plus f prime of 0 times x plus the second derivative of f at 0 divided by 2 factorial x squared plus the third derivative of the function at 0 divided by 3 factorial times x to the third plus the rest of the terms. So, since we know that f at 0 is 1, f prime at 0 is 1, f double prime at 0 is 1, and all of these are 1, we just substitute them. On the left-hand side, f of x is e to the x. On the right-hand side, f of 0 is 1, f prime of 0 is 1 times x plus 1 divided by 2 factorial times x squared plus the rest of the terms. So you end up with some polynomials, everybody. We are approximating exponential function using the sum of polynomials. In compact version, e to the x can be written as the summation of x to the n divided by n factorial, and start from 0 goes to infinity.